Hi, everybody. Today's lecture is going to be just an overview of what you'll be doing on the worksheet. If there's any questions afterward, I will open it up for a Q&A. I'm looking at the current viewer count, and it looks like there is one lucky viewer out there watching me. Two now. So hopefully people will start to trickle in. But make sure you have those questions ready. If you have any questions about the material that we've gone over and want to do a few practice problems, let me know so that we can do them. Just a little administrivia before we start. Quiz number 4 is due tomorrow, 14 May. That should be Thursday. I've kind of lost all track of time. I hope that those numbers are right. Exam number 1 is on Monday. That should be the 18th. Let me double check the calendar on that one. Yeah, that's the 18th. And then finally, worksheet number 3, which I'm going to show you right now, is going to be due a week from tomorrow. That's the 21st of May. I am still grading your lab worksheet number 2. I apologize for falling behind on that. I've had a lot to catch up on, and doing the grading and prepping the new lab and prepping your quizzes, it takes more time than I thought it would. There's people in chat. Hello. Let's do this. And then I want to click on here. And let me see, window capture. I want to capture, that's the window I want. That's not the size that I want, so hold on. Let's see here. You see my toolbar where it says BBC. That's just the news. British news, because I'm Canadian. That's probably good enough. Okay. So, if you go to the web page... Oh, you know what? I got to put this up here with this guy. So you have it. If you go to the Canvas page, you go to the Modules tab, you go to Lab Worksheet number 3. You can download Lab Worksheet number 3, which is a tutorial on how to draw molecules and how to name stuff. We have gone over virtually all of this in class with one exception, which I'm going to point out. So I typed this all up last night. It took forever. The only thing that we have not done yet is polarity. We're going to cover that tomorrow. So don't worry too much about polarity. If you are looking at the worksheet, you're like, what the hell is this? We haven't learned it yet. We're going to cover it tomorrow. But everything else should be stuff that you have learned to do, except for the naming of molecular compounds, which we'll also hopefully get to tomorrow. If not, then we'll get to it on Tuesday. Okay, so the worksheet is very simple. You're going to be asked to draw a Lewis structure of a bunch of molecules, and here are the molecules right here. And those molecules will have a Vesper geometry and a molecular geometry. And you're going to enter that into this guy right here. This is the worksheet. It's just like before. Download your own copy, or save your own copy, fill it all out, then save a copy to your desktop, and then upload it to Canvas, just like you did for the first 2 labs. I have put the file restriction on so that it only accepts XLSX files, so you do have to download it through Google Sheets. Or at the very least work in Excel, but I wouldn't want to recreate this in Excel, given how long it takes for me to recreate them anyway. Just things to note. You're going to want to fill in the number of electron groups around the central atom. We learned about how to count electron groups yesterday. We'll do an example or two in a second. You're going to assign a Vesper geometry by typing in the name, so like this. That's not a good geometry to type in, so I would not submit that answer. You're going to count the number of non-bonding electron pairs around the central atom. Tell me its molecular geometry based on that, and then you're going to tell me polar or non-polar. And then down here is just a bunch of slots for you to either write in a name or a formula. Make sure you are doing what it asks. Here it's asking to write names, so you got to put in names in this spot. And then down here you want to put in formulas. I do realize that this does not accept subscripts, just like Canvas doesn't. So when you are writing formulas, if you do something like this, that is totally fine. I will parse that as intended. Just make sure that you put the numbers in the right spots. If you need to use parentheses, use them only if necessary, just like you did on quiz number 4. Let me clear that. And there's only one page, so it's just this page. There is no second page this week. So you'll do that exercise and you'll turn it in. That's pretty much it. What else can we do? And there's the scoring key. All the questions are worth 1. Every row is worth 1, so just make sure that you do the best you can and try to avoid making any mistakes, and you'll get a good score. What else do I care about in here to go over? Not really much, because we've lectured on almost all of this. So, where is this thing? That's what I want. So we'll go boop. So, just as an example for the worksheet, I'm trying to draw on a pad of paper, and of course it's not going to show up on the screen. I got to get my tablet. Oh, I knew I forgot something. So let's do an example or two so you didn't just come out to hear me say, duh, fill in the blanks. Because that would be kind of a waste. I don't have the textbook here. Let me look up some good molecules for molecular geometry. So I can come up with a few, but I always come up with the same ones, and I want to try and avoid the ones that are on the worksheet. Alright, find me an example here that fits in this class. I could just go grab the textbook, I guess. There aren't any examples on this page. Oh, you know what I do want to do? That's what we'll do, so hold on. So let me turn this back on. So I want to show you that PHET simulator, because that is going to be something that is good to play with in this section, because it provides a simulation. I'm going to open it in its own window here. It provides a simulation of these molecules, and you could spin them around. So if you go to this website right here, and I'm going to paste it in the chat for you. So phet.colorado.edu/a bunch of stuff. If you go to that, you'll get to the page that I'm currently on. If you click on this, I believe it will try and download something. I think I already have it installed. But what this will do is it will give you 2 modes. Let me actually resize this, because this is... And for some reason I'm running on low graphics quality, probably just because I have it streaming. And it's using all my video and CPU. So what you can do with this is you can make a generic molecule, or you can pick a real molecule. I'm going to just pick this for now. And what this does is it gives you a template that you can play with. And you can drag these wherever you want to. Now remember that electrons repel each other, and electrons are in these bonds. So if I actually show this angle here, and I pull this towards it, you'll see that the number gets... I'm chasing it! The number will get small, and then the electron-electron repulsion will push it apart so that it attains the optimal angle, which for a line would be 180. Down here at the bottom, we have molecular geometry, which is written as molecule geometry, and then we have Vesper geometry, which is written as electron geometry. So, since there are 2 electron groups around this purple central atom, 1 here and 1 here, I would expect this to be linear. And because none of them are electron pairs, we would expect its molecular geometry to be linear also. Now what you can do here is you can click on these options over here, and each time you click on that, it will add to your structure. So here we go. So I clicked on a single bond and I added another one. You can also remove them. Whoop, there you go. And again, if I drag this around, it will still adopt the orientation in space that provides the most electron-electron repulsion distance possible. And as you add these things, these names will change. Now, as long as I have all the same number of groups, The electron geometry and the molecular geometry will be the same thing. Or I'm sorry, the Vesper geometry and the molecular geometry. Well, let's suppose that instead I added a double bond. Well, a double bond counts as one electron group, whether it's double or triple. Now you might look at that and go, octet rule! And yeah, we broke the octet rule by doing this, but the simulator will let you build whatever you want to. In fact, I could do something like this. I could just fill it with triple bonds, and this poor molecule. But since they all only occupy one electron group each, the geometry rules are the same. Now there is this button right here. This button is the lone pair button. When you add the lone pair to your molecule, it occupies a space. So this still has 3 electron groups around it, the lone pair and then the 2 bonds. Oops. And you can drag this however you want to as well, and it will repel from all of the other bonds. But what you'll notice down here is that the Vesper geometry will describe the shape for the number of electron groups you have. There's 3 here, so it'll be trigonal planar. But the molecular geometry will change to match that based on how many electron groups are non-bonding pairs. So because I have 3 electron groups, one of which is an electron pair, the shape is bent, just like on the table that we made yesterday, which I wish I had saved. Now you can do this with your molecules and do any combination of these that you want. So maybe we'll do something like that. Now it's upside down, but we'll do that. There's our tetrahedral sort of thing that we were playing with yesterday. And you can play around with this to see it in 3D. You can twist them around. You can spin the central atom just to rotate it. And you can see what these molecules look like. Now, as a sort of a warning on this, because some molecules go beyond the scope of this class, if you click too many times, you're going to make bigger molecules, and you're going to see shapes that you don't recognize, okay? So we don't do anything in this class with octahedral, and we don't do trigonal bipyramidal. So these are just shapes that exist but go beyond the scope of Chem 121. So if you accidentally click something in there, don't worry if you have 5 electron groups or 6. You just X those out, and you don't need to actually do them. That's going to become irrelevant when I click down here, which you can't actually see. At the very bottom of my screen is a button that says Real Molecules. And what you can do here is we can turn on these again to show the geometry. And you can choose any molecule you want to from this list to just see how it looks. Now, some of these molecules will not satisfy the octet rule. For example, BF3 looks like this. If I do XEF2, it has 5 electron groups around it other than 4. So if you see one that has 5 or 6, you should probably ignore that example. But the other ones are perfectly fine to help you practice drawing a Lewis structure and then figuring out the electron geometry. There are buttons over here that let you show lone pairs. You can uncheck that, and then the lone pairs disappear. That way you don't actually see where the electrons are, but you still feel their influence, because this over here is still being repelled by the electron pair that was there before I hit it. Okay, so that's just an interesting website that you can use to play around with. I found it really useful, and a lot of students in the past thought this was really good. You can also look up videos of molecule geometry on YouTube, where they have rendered out molecules and have them spinning around and dancing to like classical music and things like that. So make sure you use that resource, and I hope that you find it useful. Okay, this didn't really answer my question about molecules, so I need to go like this. Boop. And let me just make up a molecule. Let's do... Oh, I'm not writing on Photoshop. Hold on. There we go. Let's do this as a molecule. Let's do... Let's do that. CCl2. I'm going to give you some fancy molecules today, just for practice. We'll do these 3. That'll be a good starting point. So if we're going to draw the Lewis structure and determine the geometry of any of these molecules, the first thing we got to do is draw the Lewis structure, which means we got to invoke the 5-step plan. So this sulfur, we'll look on the periodic table and count its valence electrons. It's in group 6. It has 6 valence electrons. This chlorine, there are 2 of them, and each one provides 7 valence electrons. So my total here is, it looks like 20. Alright, so now that I know the number of valence electrons, I can draw the skeleton. And I'm just going to draw it like this because I don't actually... Oops, first of all, that's not right. Because I don't know what the geometry will be. So I'm just going to draw these out. My S is a little teeny tiny here, so I'm going to make it bigger. And I'll just connect these two. That will use up 2 lines worth or 4 electrons. So 20 minus 4 is 16. The next step was to draw valence electrons on all of the outer elements. So I'll start over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that was 16 minus 12 is 4 electrons left. And then we put the remaining electrons on the central atom. 1, 2, 3, 4. And we're all set. Let me get a different color here. That's probably good. Can we see this color? Yeah, that's fine. Alright, so now that we have our molecule drawn, we can figure out what the Vesper geometry and the molecular geometry is by looking at the number of electron groups around the central atom. So the central atom is this guy. Now I got to count electron groups. An electron group, remember, is anywhere that electrons are around the central atom. So bonds contain electrons, so a bond would count as an electron group. So there's 2 electron groups. Non-bonding pairs also contain electrons, so those count as groups too. So I have 4 electron groups. So go ahead and type in the chat what the Vesper geometry is for something with 4 electron groups. And I want to make sure that I am not picking ones that are in the list of ones that I gave you. And this one isn't. That's good. Alright. Any idea? What's the shape? What's the name of the geometry that has 4 electron groups? Gotta look at that table that we made yesterday. Hopefully you wrote the table down. Or have it handy or something. Type it in the chat. What geometry is it? Very good. Tetrahedral is correct. So we'd write that tetrahedral. That was my chair. I apologize. I hit the zoom button on accident. I gotta get a different color. That's probably okay. Is this visible? Yeah. And now what we're going to do is we're going to look at the 4 electron groups and count how many of them are electron pairs. And so here's 1 and here's 1. So of my 4 electron groups, 2 of them are electron pairs. And these are the non-bonding ones. So what would the molecular geometry be for something that had 4 electron groups, 2 of which were electron pairs? And you got to look on the table, find which one that is, and then type the answer in chat. While you do that, I will drink my soda, because it is delicious. And angular is absolutely right. Very good. So you could write angular. I'll also accept bent. Either of those is correct. I'm a little scrolling off the screen here, aren't I? Let me do that. Let me actually move this window up here. All right, so now that we've drawn our molecule, we can look and see, hey, did our Lewis structure match what we drew? And it turns out it did by virtue of me just drawing my lines at a little skew angle. So this would be better. If I had drawn my molecule before with them more straight, this would be a little more misleading. And I would say that this one that I have here, probably not the best molecule. But the one that I have drawn is okay. And since you're drawing these purely for your own usage, it is entirely up to you to draw them correctly, because I can't assess them. I'm not going to have you photograph your Lewis structure and put it online, because that's a lot of technical stuff. And also, I can't assure that or assume that everybody has a camera available or on their phone. I mean, some people might have like those old Nokia phones that are indestructible unless you like run them over with a bulldozer or steamroller or whatever. All right, that's the first example. Any questions on what we did? Otherwise, I'll just keep talking about phones, I guess. If you're typing a question in the chat, keep doing that. I'm going to go on to the next problem, which is going to be this PF2CL part. I'm going to move this, though. That's not what I meant to do. Hold on. I clicked on the one spot that I couldn't put that. We'll just put it over here somewhere. That's plenty of space. I can work with that. All right. So let's count the number of electrons in this. So phosphorus brings us 5. I got 2 fluorine, and each fluorine is 7. And I've got a chlorine, and it's also 7. So I've got 26, it looks like. If I miscount, let me know, because this is where I'm going to screw up, is counting numbers. 14, 7 is 21, 25, 26. Okay. Now I'm gonna put these down on here. So PF F CL. We'll just do that. That sounds good. I drew 3 lines. Each line is 2 electrons. That means I used 6 electrons. 26 minus 6 is 20. I'm going to use the remaining electrons to put octets around the outside atoms first. I'm just going to start over here for no reason. We haven't talked about electronegativity yet, but we'll do that tomorrow. So how many was that? 2, 4, 6, 8, 10, 12, 14, 16, 18. 20 minus 18 is 2. I have 2 left. They go on the central atom. So my molecule looks like this. And so now I can calculate the number of electron groups. So that would be these 4 right here. So 4 electron groups. The Vesper geometry is still tetrahedral. I ran out of space, so I'm going to abbreviate there. And of those 4 electron groups that I just drew, one of them is an electron pair. That's the worst looking R I've ever seen. There we go. Which is non-bonding. And so the molecular geometry, therefore, is... Type it in the chat. What could this be? What is the proper name for its geometry? Trigonal pyramidal is correct. Very good. Let's write that in. Trigonal pyramidal. And I am kind of crammed in the corner there, so there we go. Now, looking at my structure, you would look at that and not think, oh, that's totally trigonal pyramidal. So what I need to do is I need to go and change my structure so that it looks more trigonal pyramidal. And so the way that I'm going to do that is I'm going to put my phosphorus here. I've got to make more space. And we're going to go 1, 2, 3 things. So one is in the fluorine, one's a fluorine, one's a chlorine. We'll put the dots back around them like we did before. And now it looks much more trigonal pyramidal to me. And I'm going to try and illustrate that by just doing this. Here's the base of my trigonal pyramidal pyramid, which I have highlighted in blue. If we go back to the PHET simulator, I can try and make that look like, let's see here. We'll do that. So if I turn this on, and we put this over here, you can see that the molecule that we just made looks very similar to this, where the base would be right here. Now, it's important to realize that when we have a structure like this in 3 dimensions, all of the atoms can't be in the same plane. What is a plane? A plane is like a piece of paper. Like, it's just a flat surface. And if you could put all of your atoms on that flat surface, like they'd all touch it, then your molecule is planar. So something like trigonal planar. So if I did this, for example, this molecule is planar. You can see it's flat. I'm looking at it from the side, and everything is just flat. You couldn't tell that there was an atom behind that unless you rotated it like this. But when I put this guy in here, you can see that it's no longer planar, and it is now in 3D. So a question could be asked on an assessment, maybe like the Chapter 5 quiz or something. Is the central atom on the same plane as these hydrogens? And the answer would be, well, no, it's a little higher because these guys come down, as you can see here. Let's go back and do the last one. Then we'll ask for more questions. Some of the molecules on your worksheet are going to have... I gave you the wrong molecule. Hold on. I had an idea in mind, but I gave you the wrong molecule. Just a second. So I want C2. There we go. Actually, this might be too complicated. Let's not do this. I do want to do the C2. I just want to make sure I don't give you one that is... Yeah, let's do this. Okay. C2Cl2. That's what we'll do. Now, if you have a molecule where the first atom has a number that isn't 1, then what that means is that there isn't really a central atom, so to speak, because I'm going to have a C, a C, a Cl, and another Cl somewhere, and I don't know where to put it for now. Generally speaking, with these molecules that you're going to get, what you'll want to do is arrange them so that they're symmetric. Okay, so something like this would work. If I did something like this instead, now it's not really symmetric. Like, the C over here is alone, and he's like, well, what am I going to do? Boo-hoo. So try and make your molecules have as much symmetry as possible for this class, because that'll just simplify things. Oh, we didn't count electrons. Hold on. So there are 4 electrons per carbon and 7 electrons per chlorine. So I have 8 plus 14 is 22. And I used 6 to do this, so now I have 16. 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4. 3, 2, 1, 0. Uh-oh, this guy doesn't get an octet, so we gotta fix this. So when we got to step 4, which is put electrons on the central atom, I ran out. I didn't get to give an octet to the inner atoms. One of them did, but the other one didn't. So step 5, remember, is we got to start making multiple bonds. And given it that this is the carbon that needs them, and I want to make my molecule as symmetrical as possible, I have some options, but one of them is going to look better than the others. And it turns out the better option is the correct option. So I could move that electron pair right here. And I could then move this electron pair right here. And I have this as an option. Or, and I'm just going to draw the molecule real quick how it was. So dot, 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 dot. I could move this one like I did before. Or I could move that one over here. And now right off the bat, looking at these, and actually, you know what, I should make this the same color up here. Which of these just looks better? The top one or the bottom one? There's something about the bottom one, isn't there? Like, it just looks off. There's something wrong here. One of my CLs has a double bond, but the other one has a single bond. One of my carbons has an electron pair and the other one doesn't. There's something odd going on here. And if you look at your structure and it just looks funky, like you don't have symmetry, then odds are that you have made the bonds in the wrong way. Now, that's a very kind of like touchy-feely, like, how do you feel about your molecule sort of assessment, which is not really scientific. There is a way to determine this using a rule called formal charge. We don't cover it in the textbook because it's just a lot of extra rules that help you more for more complicated molecules. But for simpler ones, it just gets in the way. Oops, I dropped my pen. Hold on. So if you look at your molecule and you have 2 different ways to do it, choose the one that has more symmetry and just looks better, if you have an option. Sometimes you'll draw a Lewis structure and it'll just be like, well, I can put the double bond on the top or the bottom or on the side. Which one should I pick? And it turns out they're all the same anyway, because you can just spin it around. In those cases, you just choose any answer and it's fine. So that would be the structure for this molecule. How would we assign it a geometry? So let's erase this part. We'll just go boop, boop. How would I assign this a geometry? And the answer to that is you need to elect something. That's not the pen tool. To be the central atom. And relative to that, you can now determine the Vesper geometry and the molecular geometry. Because if this is my central atom, how many electron groups are around it? Well, here's one, and here's one. So that's 2 groups, so this is going to be linear. Of those 2, none are electron pairs, so its molecular geometry will be linear as well. Alright, those are the examples I had prepared. And if I say prepared, that's actually being very generous. Those are the examples I came up with in the last 20 seconds. Do I not count the other groups? So you mean on, say, let me get a different color here. So do you mean this one right here? So we don't count that one in the same way that we don't count these electron pairs, because they're not on the central atom. Even though in this case, we're going to put these little air quotes around it, because we didn't choose them to be the central atom. So we ignore them. Now, that geometry is only true for this region of space. So what this is telling us is that the geometry from this C to this chlorine and to this other C will be linear. What happens past that could be anything else. And so what we need to do in that case is we need to then consider a different central atom. So if the red arrow right here became our central atom, we could then do the exercise again. And we would say, well, this is an electron group, and this is an electron group. They're both 2, so I have linear and linear again. So this entire molecule is linear from both central atoms. But that won't always be the case. So for instance, I'm going to delete everything here, so make sure you get everything you need. As molecules get larger and more complicated, they have different geometry based on where you choose the central atom to be. So for example, and I'm going to go select all, delete. So if I drew a Lewis structure that looked like this, for example, so where's my pen? That didn't work. I didn't mean to put that extra line there. Actually, let's do... I just want more things in here. I don't know. Maybe this is a molecule. Because you can make anything into a molecule. You can connect any atoms together that you want to. And if I asked you, what's the geometry of this molecule, you would look at me and you'd be like, well, don't be ridiculous. I forgot 2 electron pairs up here, but that's okay. How the hell am I supposed to tell you what shape this is? It looks like a really long-headed dog. I don't know. That's not a geometry that we know. Instead, what we do is we elect a central atom. So I'm going to call this number 1. And so at number 1, how many electron groups are there? Well, there'd be this one, and this one. So if there are 3 electron groups, its valence or Vesper geometry would be trigonal planar. And its molecular geometry, since none of those around that central atom were electron pairs, would also be trigonal planar. And then we could grab a new color, and we could look at number 2 here. So this one's number 2. How many valence electrons are around, or not valence electrons, I'm sorry. How many electron groups are around number 2? Well, I've got this one, which I'll double count. This one, and this one. So at number 2, the Vesper geometry would be tetrahedral, because there are 4 electron groups. My computer's starting to slow down. And its molecular geometry would also be tetrahedral, because none of those are electron pairs. I think this molecular simulator is eating up my CPU, so... doesn't like to stream and do things like that at the same time. And then I could say, we'll get another color here. We'll just pick this one. And we'll pick... yeah, let's not pick that one. Let's pick this one. So if this is number 3, how many electron groups are around this guy? Well, there are 4. So at number 3, the valence geometry, or I'm sorry, the Vesper geometry will be 1, 2, 3, 4 groups, so that's tetrahedral. But of those 4, 2 are electron pairs, so its molecular geometry would be angular or bent. So that's how you could do that for a much larger molecule. You just have to elect which ones you want to be the central atom. And you could, in theory, do this for all the atoms that are connected to some other atom and determine their geometry that way. So that was a good question. Thank you. Other questions? Any questions at all? Well, it's pretty quiet in here, so... Nope. Here's what we'll do. I'm going to put the title card back up. And if you're all set for now, then that's all we'll do for tonight. I will put the break timer up just to have it going. And I'll let this count down for a little bit. And if nobody posts any questions in a few minutes, then I'll just turn the stream off and we'll call it a night. You can also chat in the chat box there. And if you come up with a question that I can answer in text, I will just type the answer to you. But we'll call it a break, and then after 10 minutes we'll reevaluate. So I'll turn the music back on, and I'll see you in a bit. Hi, everybody. Looks like I didn't get any feedback, so I'm going to be taking the stream down. I just want to wish everybody a happy evening, and I will see you tomorrow for our continuing lectures in Chapter 5. Have a good night.